Alright guys, so we're going to start our unit with an introduction to normal distributions. This entire unit will be about normal distributions. So this is kind of just an introduction to how those will work. The learning targets for this lesson are: I can differentiate between discrete and continuous data. Okay. I can find relative frequencies and draw distributions for continuous data, and I can interpret the data to make inferences. So after this lesson, you should be able to do these three things. Alright, so let's get some definitions out of the way. First of all, discrete data is data whose possible values are countable and finite, meaning like ACT scores. You can't get like a 27.5. Okay, you can only get whole numbers and they're all countable. Okay, you can't, people in a class, you can't have 2.5 people or something like that. Whereas continuous data, okay, continuous data is data which can take any numerical value within a certain interval. For example, the height of people. Okay, well, I can be 6 feet and a half inches, okay, or 6 feet and a quarter inches. Okay, all of those are possible heights. Okay, distance between cities. You can be 2.3 miles away from a city, or you can be 7.8. Okay, all of those numerical values can be achieved in continuous data. You can kind of think about, back when we talked about discrete and continuous graphs, that remember that when we had a graph and it was discrete, it was just a bunch of points, okay, that jump from point to point, whereas a continuous graph, okay, you don't jump from point to point, you connect all the dots. Same way here, where a discrete data jump from all the whole numbers, and then continuous data, okay, connect all the possible values. Okay, we're also going to be talking about the difference between the population and the sample. Okay, populations represent all the possible data in a study or a survey. A sample is something that we take out of the population. Okay, so population might be the entire school, and then a sample could be like the students in my class. Alright, now we have relative frequency. The relative frequency is the ratio between the number of occurrences within an interval to the total number of occurrences. So in other words, I'm going to take the number of occurrences for what I'm particularly looking for out of the total number that happened. So in the next example, we'll be finding relative frequencies for mile times and 100-meter dash times for a given PE class. Alright, so let's start with this example. Notice that I have all these different intervals over here. Okay, a mile time of 4 to 6 minutes, a mile time of 6 to 8 minutes, a mile time of 8 to 10, 10 to 12, and 12 to 14. So if I want to figure out the relative frequency, first of all, I need to know the total number of students. Okay, so if I just add up 2, 7, 15, 10, and 4, I get a total of 38 students in this class. Okay, so if I'm going to do the relative frequency for 4 to 6 minutes, what I'm going to do is I'm going to do 2, if I can write, divided by 38. So if you do that in your calculator, 2 divided by 38 is about 0.05. So this is going to be 0.05. Okay, and so then I'm going to do the same for everything. So 7 out of 38 would be the next one. Okay, notice that I always do it out of the total. Okay, so 7 divided by 38 is about 0.18. Okay, I will always have you round to 2 decimal places. just because it's really easy to convert to percent after that. All right, the next one is 15 out of 38. 15 out of 38, and that would be 0.39. Okay, the next one is going to be 10 out of 38. 8. Okay, 10 divided by 38 is 0.26. 6. Okay, and then the last one, 4 divided by 38, is about 0.11. Okay, so I round that up to 0.11. Okay, if this is done correctly, these relative frequencies should add up to very, very close to 1. Because if you imagine, these are all the percentages out of 38. So if I have all the percentages, I should have 100% of my data. So if I take 0.05 plus 0.18 plus 0.39 plus 0.26 plus 0.11, I get 0.99, which is really, really close to 1. All right, so notice that in this data, what it's telling me is that a lot of people, 39% of people ran the mile in between 8 to 10 minutes. Okay, that's what this number represents. Likewise, all of these represent the percentages of the people in between the interval. So 26% ran between 10 and 12 minutes, 5% ran between 4 and 6, and so on. Okay, so I'm going to find the relative frequencies for the other. It might be beneficial to you to pause and try to find them on your own and see if you get the same things as I do. Okay, so this is the same class, so I know that the total is still 38. Okay, you can check on your own if you'd like to, but I'm going to do 1 out of 38, which is, let me get my calculator real quick. 1 divided by 38 is about 0.03. Let me erase that. Let me write that better. So 0.03. And then we have 10 out of 38. Whoops, I wrote 13. I don't know why. Okay, so we have 10 out of 38. That's an 8. 10, which we actually already have over here, right? We already have this 10 out of 38. So we might as well just copy over 0.26. Okay, and then we have 13 out of 38. 13 divided by 38 is 0.34. And then 9 out of 38 is 0.24. And then 5 out of 38 is 0.13. Okay, again, you can check to make sure that that adds up to close to 1. So 0.03 plus 0.26 plus 0.34 plus 0.24 plus 0.13, and it in fact adds up to exactly 1. Okay, so that is how you will always find relative frequencies. All right, so that last part relates directly to the first learning target. Okay, it was all about being able to find relative frequencies. And this next part is about graphing those relative frequency in a histogram. So what you're going to want to do, we're going to do mile times first. So what I need to do on my x-axis here, okay, down here at the bottom, is I need to create my intervals. So if you remember, my first interval was from 4 to 6. So what I'm going to do is I'm going to say that this is about 4, okay, and then this is going to be 6, and then I'm going to have one from 6 to 8, and I'm going to have one from 8 to 10, and then from 10 to 12, and from 12 to 14. Okay, so here are my intervals. Okay, on the y-axis, Okay, these are going to be all my relative frequencies. Okay, so again, if you look at our data table, okay, these are all going to be measured in minutes. Okay, and then this is the relative frequency over here. I'm going to erase that. Alright, so we're going to go there. We're just going to call this RF. So the relative frequency. So what I'm going to do, so I'm going to count by like 0.1s. So for example, this first mark is going to be 0.1, 0.2, 0.3, 4, 5, 6, and if you have to, you can go higher than that. But for this example, I don't need to. So that's 0.1. This is 0.2, 0.3, 0.4, 0.4, if it'll write. Okay, 0.5 and 0.6. Okay, so if you remember from the data table, which you should have written down in your notes, okay, between 4 and 6 minutes, I had a 0.05, a 0.05 relative frequency. So that's right in between 0 and 0.1. Okay, then for 6 through 8, I had a 0.12, which is really close to 0.2. So it's going to look something like that. Okay, and then between 8 and 10, I had 0.39, which is almost 0.4. So I go up almost to 0.4, over, and down. Okay, and then from 10 to 12, it was 0.26. So it's kind of like right in the middle of 0.2 and 0.3. Okay, and then 12 to 14 was 0.11, which is almost right at 0.11, maybe just a little bit bigger. Okay, so this is a histogram that displays my data for mile times in this given class. So my relative frequencies are over here on the y-axis again. Here are my minutes. Okay, so as you can tell, most of my data lies here in the middle times. Okay, between 6 and 12 minutes is the majority of my data. Alright, so we're going to do the exact same thing, but now we're going to do it for 100 meter dash times. Okay, so now my x-axis is going to be measured in seconds. Okay, because as you can tell from the data table on the last slide, that our times were measured in seconds. So what I'm going to do, I'm going to go from 9 to 10, from 10 to 11, from 11 to 12, from 12 to 13, and then 13 to 14. 14. Okay? And for the same thing, on the y-axis, I'm still going to do my relative frequency. Okay? Relative frequency is going to go this way. So I'm going to start again with like 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. So 0.1, 0.2, that's going to be kind of hard to see, but it's 0.2, 0.3, 0.4, 0.5, and 0.6. Alright, so if you look at your data table from the 100 meter dash time, 0.03 was between 9 and 10. So that's going to be like somewhere in here. Okay, so a really small rectangle. Okay, for 10 to 11, I had 26. So that's going to come up here and be pretty much in the middle of 2 and 3. Okay, and then 11 to 12 is 34. That's going to be way up here in between. Actually, I think I went too high. It's going to be in between 3 and 4. So it's going to be like somewhere in here. Okay, and then 24 is going to be somewhere in here. between 20 and 30. And then between 13 and 14 should be 0.13, so it's going to be somewhere in between 0.1 and 0.2. Okay, so that's all you have to do to make a histogram. Okay, just make sure that your relative frequency is always your y-axis and your other data is always your x-axis. And then you're just graphing the intervals in rectangles like these. All right, so that covers the second learning target for the day and being able to make a histogram based on your relative frequencies. So the last one is going to be talking about interpreting relative frequency histograms. So the objective is not just to be able to make a relative frequency histogram, but to understand what that information is telling us. So what you're going to ask yourself are these three questions. Okay, what is the overall shape of the histogram? Is it symmetric, meaning that there's a center point and it looks the same on both sides, or does it have a skew to one side? So that means, is most of my data to the right, or is most of my data to the left, or is it all centered right in the middle? Okay, also we're going to look at how many maximums we have. Okay, does it have one main hump in the middle, or does it have multiple places where the data goes up and then goes back down? Okay, and then finally, how spread out is our data? Is most of our data in the center, or is it spread widely over a long span? So we're going to go through some examples of what we would say about our data. So let's look. Okay, so here are two examples. If you look, notice first of all that the first question that we're supposed to ask ourselves is it symmetric? And notice that this first one is definitely symmetric. Okay, right here in the middle, okay, right here at 200, okay, it looks like it perfectly maps to itself if you flip it over the middle right there. Okay, this one only has one maximum. Okay, notice that its maximum is right up here. Okay, so it kind of goes up, hits a maximum, and then kind of goes back down. Okay, and notice that a lot of my data is in the center. Okay, it's definitely has centered data. Most of my data occurs all right in here. Okay, it's not spread out over a lot of different lengths. Okay, now for this one, notice that it's not symmetric. Okay, there is no line that I can fold this over so that it matches up to itself. Okay, so this part of the graph is a lot different than that part of the graph. Okay, notice that if I draw my little something like this, notice that I have two maximums. Okay, here and here. Okay, so two maxes. Okay, so what we call that, and if you ever go on to AP Stats, is we call that bimodal. Okay, so it has two maxes. Bi coming from the fact that it has two maxes. Okay, and notice that the data is spread out. Okay, so I have a lot of data between 4.5 and 5.5, but I also have a lot of data between 7 and 9. Okay, so it's spread out over two intervals, a lot of my data being in here and a lot of data being in there. All right, so then we're going to look at two different kinds of distributions. This one is a skewed right, and this one is a skewed left. Okay, so as you can tell, these are not symmetric. Neither of them are symmetric. Okay, because they're both what we call skewed one way or the other. Okay, so not symmetric. Okay, they both only have one max. Okay, kind of like our first example. Okay, so if you notice, this one goes up and then down like that. This one goes steadily up and then fast down. Okay, so one max up here and up here. Okay, this one, okay, when you look at the spread, these are kind of spread out, but notice that a lot of data happens within a small area. So I would say that these aren't really spread out, but all the data is to one side. Okay, so they're one-sided. Okay, now what this tells us is that most of our data, for example, in the right one, okay, most of our data occurs between what looks like about 0 and 50. Because 50, imagine, is in between 0 and 100 here. So look how much data is contained within 0 and 50. Whereas this one, a lot of data is between like 60 and 90. Okay, that's almost all of my data. This is a very big frequency in here. All right, so just to revisit the learning targets that we were supposed to meet, okay, I want you to ask yourself and kind of self-evaluate, how confident are you that you can do the following? Can you differentiate between discrete and continuous data? So if I gave you an example, would you be able to tell me, oh, that would be discrete or that would be continuous? Okay. If I gave you a table, could you find relative frequencies and then draw the distribution for the data? Okay, so how confident are you that you could draw the distribution in a histogram like we did? Okay, and then lastly, using that data to interpret what is actually happening in that data set. So is it skewed to the right? Is most of the data to the right? Is it to the left? Is it centered? Okay, all those sorts of things we need to be able to do in order to move on. Okay, so if you feel confident that you can move on, okay, your assignment is to do 15.1, problem 1, questions 1 through 3. Okay, so if you haven't grabbed that yet, come grab it from me, and you can work on that. If you don't feel confident in these 3 things, please let me know, and I can give you extra support on how you would do those.